Everyone, so I want to continue on with the 2018 AP Physics C Mechanics free response question. I'm going to go with number two, which, as you remember, should be the conservation question. So, conservation of energy and conservation of momentum are pretty much the things that we want to be thinking of. Now, right off the bat, we can already see that part A of this question is going to have us do integral calculus. Now, I always recommend that you practice these questions first. So make sure that you follow the links in the description below to check out both the questions and the answer sheet, so you can kind of work on this yourself. But continuing on, so we're gonna actually have to use calculus for this. We didn't have to do it in the previous question, if you recall. For question one, I had mentioned that you could have used it, but it wasn't necessary. This time, it is very obvious that I have to do it, both for the fact that the force that's being given to us is changing over time, and because they straight up tell me use integral calculus. So if you look on the reference table, the equation that solves for impulse is going to be the integral of the force with respect to time. So what I'm going to do is I'm going to use the force equation that they gave me, 3,200 t squared minus 500 t dt. I need to put my bounds here. So seeing as this question basically goes from 0 to 0.16, and let's see if they mention it. I don't see it really mentioning in the question, but the graph pretty much ends there. So I'm going to use that as my bounds. So 0 to 0.16. So I'm going to integrate this. If you recall, I add 1 to the exponent, so this becomes a 3, and then I divide the coefficient by 3. So 3t cubed minus, add 1 to this exponent is 2, so this is going to be 500 divided by 2, t squared. I'm not going to put the plus c because I know when I evaluate this between 0 and 0.16 that it's going to cross out anyway. So what I end up getting, let me just, okay. So this one actually doesn't really have that great of a conversion. I guess I'll just leave it as is, 3200 divided by 3. And this is going to be 0.16 cubed. This is 250, 0.16 squared. And then I know that when I plug in 0, that's a 0. When I plug in 0, it's just going to be 0 minus 0. So this whole thing drops down to 0. When I do this and I plug this into the calculator, I end up getting 4.37 minus 6.4, which if I subtract these, I end up getting negative 203 Newton seconds. All right. This is a 3-point question. So this question was worth 3 points. You got 1 point for noticing that, or not noticing, but setting up the integral part. So basically just writing in the equation from the reference table and then plugging in the equation that they gave us. You got 1 point for integrating between the bounds. So if doing the integration and then making sure that you plug in the bounds. And then you got 1 point for this. And as long as this answer kind of makes sense with the work, you might get that point back. So just be aware that of the 3 points, you could easily have gotten one of them without even doing any real work. All right. So now for part B, they want us to find the speed of the car after the collision. I think the easiest way to do this is use the other form of the equation for impulse. So we have, so actually I will point out that You probably could get around, if you for some reason felt the need to do it. You could have rewritten this equation so that it was acceleration, divide by the mass, and then you could have integrated that and then figured out what the speed is at the very end at 0.16 seconds. That's way too much work. Keep in mind that the parts are usually being asked for a very specific reason, so that one part leads into the next. It may not lead to the very next thing that you do, but it will be leading to something that you use later on. So for here, when they want the speed, I'm actually going to use the impulse and the other part of the equation for impulse, which is that by definition, it's a change in momentum. So this is going to be equal to m delta v. So I know my impulse is negative 2.03. I know my mass is zero point 0.5. I don't know what I'm looking for the final velocity, and then they tell me that cart 1 was moving with an initial speed of 3 meters per second. So this is going to be minus 3. All right, so what I can do is multiply both sides by 2, and I get negative 4.062 if I want to be really accurate. I could add the 3 over to the other side. And I end up getting negative 1.06. This is going to be meters per second. So that's this part. And then the second part says, what direction is it going to move? Let's see. It says that it was moving 3 meters per second towards cart 2. So that's to the right, based off of the diagram. Since my velocity here is now negative, that means it's going to go in the other direction, which is going to be to the left. Now, all together, this was worth 2 points. 1 point for pretty much all of this, and 1 point for this. All right. For part C, they want us to find the speed of cart 2 after the collision. There's a few different ways that you could go about doing this. If you wanted to, the way that I usually teach my class is, I would actually just do mv of the first one equals m1v1 plus m2v2. I know that this object was initially 0.5 times 3. I know that this is now going to be 0.5 times negative 1.06. And this is now going to be 1.05 times that unknown speed. So plugging this in, I get 1.5 here. This will end up being negative 0.53 plus 1.05 V2. Doing the math and the algebra, adding things over and then dividing by the 1.05, I'll end up getting 1.93 as my final answer. I could also have, what I could have done is realize that because this is a collision and conservation momentum, that the impulse of cart 1 is equal and opposite to the impulse of cart 2. This actually comes straight from the Newton's third law. So the force that one exerts is equal and opposite to the force that the other one experiences. If we multiply both sides by t, we end up getting the impulse equation. So it comes straight from Newton's third law. I could have done this and basically said that for object 2, it was instead of negative 203, it would have been a positive 203 times the mass 1.05. It started at 0 initial velocity, so the change in velocity actually would just be its final velocity. And then if I divide 2.03 divided by 1.05, I end up getting the same 1.933. So that was another way of doing this. It's whatever floats your boat. You end up getting 1 point for essentially one of these conservation laws, either saying that the impulses were equal and opposite, or just doing the conservation momentum equation. And then you get 1 point for substituting the numbers in and getting an answer. So essentially, these two lines. So plugging the numbers in and getting the answer gets you that second point. Now part part C2 wants us to show that the collision is elastic. Now, if you recall, there's two different types of collisions. There's elastic and inelastic. Elastic collisions mean that the kinetic energy is conserved. So what they want me to do is find the initial kinetic energy, which is just 1/2 object 1 times its speed. If I plug the numbers in, I get 1/2 of 0.5 times 3 squared. This just ends up being 2.25. After the collision, it's going to be the sum of both of these. Now, object 1 has a negative velocity, but I do not care about that. It's going to be squared, so that actually doesn't really matter. 2 squared. So this is going to be 1/2. I'm actually pulling out the 1/2 so I don't have to keep writing it. 0.5 times 1.06 squared plus 1.05 times 1.93 squared. Sorry for the closeness. So plugging all this in, 0.5 times 1.06 squared plus 1.05 times 1.93 squared. I end up getting that the final kinetic energy is 2.24 joules. This is pretty much close enough for me to say that the kinetic energy initially and the kinetic energy at the end are the same. The only reason why there is a slight difference is simply just because of my rounding. Had I kept the final velocity of either of these objects a little bit further out, I probably would have gotten an exact answer. So that's how I would show that this is elastic. So this question was worth 2 points. You got 1 point for so you got 1 point for basically realizing that these should be equal, and you got 1 point for just doing all the work, getting the kinetic energy initially and finally. So that was the other point. Part D, they want to find the speed of the center of mass for the two cart spring systems. Okay, so the easiest way that I can find as far as finding the speed of the center of mass is to pretend as if this was not an elastic collision, and instead consider this to be a perfectly inelastic collision, or a totally inelastic collision where they actually stick together. So what I'm going to do is I'm going to do this same thing, except I'm going to say that they end up with the same final speed. If I do this, I get, 0.5 times 3 equals 0.5 plus 1.05 times V. Dividing that, so 0.5 times 3 is 1.5. Divide that by 1.05 plus 0.5 gets me a center of mass speed of 0.9. It's gonna do it to 2 sig figs, but I'll do it to 3. I get 0.968 meters per second. This question was worth 2 points. Essentially doing 1 point for this and 1 point for this work. All right, and then the very last part is this part two. Find the maximum elastic potential energy stored in the spring. Um, all right, so one of the ways that I could do this, there's two different ways to do this. One of them is to use energy and basically set the initial kinetic energy of the system equal to here. I'll just write it out. You could have done the kinetic energy of object one initially equals the kinetic energy of essentially the center of mass plus the spring potential. If you do this, you would end up getting 1/2 m1 v1 0 squared, 1/2 of the total mass m1 plus m2 vcm squared plus the 1/2 kx squared. If I do this, the halves drop out. I could plug my numbers in. I know what the k is. It's up here. Um, Actually, I don't know why I'm plugging this in. Sorry, I misread the question. I thought it said the maximum compression. I'm actually going to leave that as US. If I do that, I'd end up getting my answer. So this would, I wouldn't actually be able to drop out the halves anymore. Um, but if you do this, I don't feel like writing it all out right now. So we already said that this was 2.25, and this is going to be equal to 0.726. So subtracting it over, I end up getting that this is going to be 1.52 joules. This was a 3-point question. You got 1 point. If you used this method, you would have gotten 1 point for this, 1 point for the substitution, 1 point for the answer. Now, if you didn't want to do it this way, another way that you could have done it is realizing that the total change in potential energy of the spring is the same as the work being done by the spring. Work is the force. So you'd have to. They're looking for a maximum. You'd have to figure out what the maximum force is. So you'd have to. Actually, now that I'm thinking about this, actually wouldn't be a lot easier because you'd have to take the derivative of this in order to find where the max value actually is, and then use that into the fx equals kx equation. Yeah, so actually, I think this one's probably the easiest way. Uh, and that's about it. So really, only one question actually required calculus. Everything else was really straightforward. And for the most part, like I said, it played off the idea of conservation. So if you have any questions, feel free to let me know. Otherwise, good luck. Have a great day.